We left off on the 29th. I can't remember if I promised that we needed to do more examples. Okay, so we did one-to-one and onto using mapping diagrams, but not quite with graphs. Okay. Thank you. So we're going to continue on in section 7. We won't even finish section 7 today even, so we still have another day in this section. So previously, we had talked about operations of functions, including composition. But really, we talked about composition mainly so we could talk about inverses. And we were wanting to answer the question of, was there a way to predict when a function's inverse would itself be a function or not? And we saw that there was 2 criteria that needed to be true for that inverse to be a function. So if the function was one-to-one and onto, we have those both together, we call it a bijection. Then that function's inverse is guaranteed to be a function. If we lack one or the other, we're going to fail to be a function. So, if you remember, when we say onto, what we really mean is that the whole range is used. And when we say one-to-one, we mean that each y is used only once. Bijection. And what I think I still owed you guys was some examples of looking at graphs and deciding if they were, the function represented by that graph is one-to-one or onto or both, right? So let's do some examples of that before we move on. So first thing I should mention is when we're given a graph, you can assume that the function it represents is a function from the reals to the reals. So the implied domain and range would be all real numbers kind of thing. Here, unless there's like an asymptote or something drawn in, I guess. So here, let's start. Is this, well, clearly this is a function, right? Everybody agree with that? Okay. Is it onto? So the way I like to think about onto is I look at the y-axis, and I say if I pick a value on the y-axis, can I track over and find a point on our graph that contains that y-coordinate? If the answer is yes for any point on the y-axis, then it's onto. Thank you, sir. If I can find Jacob Anderson, if I can find any point where that's not the case, then it's not onto. Everybody okay with that idea? So this is definitely onto, right? Everybody agrees with that? That no matter which y I pick on the y-axis, I can find a point that has that exact y-coordinate. Is it one-to-one? Yes. How can you tell? Good. Each y is only used once. What would it look like if a y was used twice, Ben? Yeah, you'd have like a situation where it would fail a horizontal line test. So any horizontal line I draw intersects the graph exactly one time, in that case, I can tell it's definitely 1 to 1 because if a y-coordinate was used more than once, it would have to intersect that horizontal line twice or more. Good. Everybody feel okay on that first one? So that first one is 1 to 1 and onto. We could also call it a bijection since it's both 1 to 1 and onto. Very good. Let's look at another. Let's use a color here. Is this onto? Yes, right? If I look at the y-axis, no matter what point I pick on the y-axis, or what y value I pick on the y-axis, there's some point on our function that has that y-coordinate, right? Everybody agree? Okay. Is it 1 to 1? No. Why not? Yeah. There are definitely y-coordinates that are used more than once. For example, if I drew that horizontal line, I see that there's 3 points that have that same y-coordinate. So it's definitely not 1 to 1. Everybody feel okay there? Is this onto? No. Why not? Yeah, there's lots of y-coordinates down here that if I tried to find a point, there is no point with that y-coordinate. Very good. Is it 1 to 1? What do you guys think? 1 to 1, yes or no? Yes, right? There's no y-coordinates that are used more than once. Any horizontal line I draw intersects the graph at most one time. So this one definitely is 1 to 1. Everybody okay there? How about this one? Is this onto? No, right? What's the problem? Yeah, we have a big section of our y-axis down here that if I pick this y-coordinate, there's no point that has that y-coordinate. Is it 1 to 1? No, right? If I draw a horizontal line, there's definitely spots where the graph intersects it more than once. Do we feel okay about picking out the 1 to 1 and onto from looking at a graph? Not so bad, right? Once you figure out kind of what you're looking for, like what the words mean visually, it's usually pretty easy to pick that out. Although not always obvious, like what would I be looking for from the words? Going from words to the image is sometimes a little bit tricky to figure out, like what should I be looking for? Because it is a very visual exercise. Okay. So last time we had been talking about inverses, and we had looked at finding inverses when our function is represented as a mapping diagram, right? We did a bunch of examples where we found inverses from mapping diagrams, and we used the 1 to 1 and onto to kind of justify why we needed those two conditions to be sure that the inverse would be a function. You guys remember that from last time, or at least sounds familiar enough? Okay, good. what I want to do today is I want to talk about some other representations of a function and how to look at those, find the inverses, determine whether the inverse should be a function or not before actually finding it, looking for one-to-one and onto and that sort of thing. Okay with that plan? So one way or another way we can represent a function other than a mapping diagram is with something like this, so like a set of ordered pairs. So let's, before we actually find the inverse here, let's predict, just by looking at f, whether we think the inverse will be a function or not. So to determine that, we need to check to see if f is one-to-one and onto. So let's start with the easier of the two questions. Is this one-to-one? Yes. Good. What are we looking at? Good. There's no y that's used more than once. We're looking for a repeating y coordinate. If I look at the y coordinates, there are no repeats. So this is definitely f is one-to-one. Everybody agree here? The onto part, when we're given a set of ordered pairs like this, is a little bit tricky. And it's really only tricky in regard to like what kind of assumption we should be making. In the case of a set of ordered pairs like this, we can assume that the relevant domain is the same as the implied domain. And in that regard, the relevant range is the same as the implied range. So, in the case of a set of ordered pairs, unless you're given like a big preamble, you can probably assume that it's onto without any real hassle. And I'll give an example in a minute of what kind of information you have to be given for you to say that this particular function was not onto. But I want to just move ahead with, if all you're given is the set of ordered pairs, say it's onto and just keep on going. So, if I know these two things, I know that f inverse is a function. And how would I write f inverse? Very good. So I can write f inverse as just a transposition of the ordered pairs. The word transpose is just fancy math talk for trading places. The two things switch locations. So we just transpose x and y, or swap the x's and y's. Just being fancy. Now, had instead you be told that so if you were given this preamble where it says f is a function from the set -2, 0, 1 to the set 5, -3, -1, 0, where f is the ordered pairs -2, 5, 0, -3, 1, -1. If you're given this sort of information, now we have to actually sit and look carefully about whether f is onto or not. Because you're given the implied domain and implied range here. What you have to do is to check to make sure that that entire, in this case for onto, the entire range is used. But that's not too difficult, right? So the from location is the domain, the to location is the range. If I look, there is an element in the range that isn't used in the function. So for us to say a set of ordered pairs is not onto, you'd have to be given kind of that implied domain and range, and make sure, and then all you have to do is make sure that the relevant range matches the implied range. It's a little caveat, but not terribly tricky, but if you hadn't seen it, determining if the other one was onto just doesn't, it's kind of a difficult question since you don't know what really the mapping is. Let's look at some graphs now. So if this is my function f of x, I can see right away that it's not one-to-one and not onto. So I can tell right away that f inverse is not a function. Everybody agree with that? Now, I want to be a little bit technical here. The most important one for us when looking at graphs is the not one-to-one part. If we're careful on how we're going to define things, we can recover from the not onto. We have to be a little bit sneaky about what we're doing, but we can certainly build out an inverse that's still a function. If we have one-to-one but not onto, we can fix that with a little bit of careful defining of the implied domain and range. But the one-to-one part is the part that we really care about. So if I want to find the graph of the inverse, probably the easiest thing to do is to just define a few ordered pairs on my curve and then swap the x and y coordinates and use those for graphing. Everybody okay with that plan? Seems like the easiest way of going about it, right? How many points should I pick here? This is a parabola, so I need at least how many? At least 3. Good. And can I pick any old 3 I want? Or does there have to be some kind of requirement? What if I just pick those 3? Would that be enough for me to draw the inverse? No, right? So I have to be a little bit more careful than that. What point for sure do I need to have? Starts with a V. The vertex, I would definitely want the vertex. So let's say that that was the point that we read off as the vertex. The other 2, is there any restriction on how I would find or pick the other 2 points? A little bit of one. What would I need to make sure I do with choosing these other 2 points? They should be on different sides of the vertex, right? Or else I wouldn't be able to for sure know where to put the other arm of my parabola when I draw this. Does that make sense to you guys? So, I don't know, like I'll pick one from over here, and then maybe one from over here. So if I redraw this then, so negative 2, 5 becomes 2, negative 5. Nope. Becomes 5, negative 2. Goodness gracious, Kulak. What are you doing? And then 0, negative 3 becomes negative 3, 0. And then 1, negative 1 becomes negative 1, 1. So I got something that looks like this. Is everybody okay with that idea? If you were to describe to me visually, what did we do to turn f into f inverse? What would you say? Okay, but what if you weren't? If you were given a graph with no labels and no coordinates labeled? Like there's no tick marks on the axes and no coordinates labeled, and you're just trying to do it from the shape of the graph and have nothing to do with the coordinates at all. What would you say here, Ben? Okay, so Ben says you kind of turn it to the side, which is kind of what we're seeing happen, right? Is it just looks like you spun it a little bit? Leonie? So it looks like there's some kind of rotation that happens. In fact, you could make that argument. It's a little bit easier to see it, though, if we think about it as a reflection. And what we're reflecting across is this line y equals x. So if I reflect across that line, 0, 3, or 0, negative 3 would go to there, which is negative 3, 0. 1, negative 1 goes to there. And then negative 2, 5 kind of goes to there. Can everybody see that? Notice that when I drew these lines doing the reflection, these are all perpendicular to that line, y equals x. But that's a geometric description kind of what's going on there. Does that sound familiar? I'm sure that we mentioned doing this graphically by reflecting across the line y equals x before. Although from a practical standpoint, it's often hard to draw that, as opposed to just picking coordinates and, transposing the coordinates and then sketching in the in-betweeners. Any questions about drawing the graph of an inverse? Okay. What if you were given a function represented algebraically? So if I was given my f of x as an equation, does anybody remember how we find the inverse of a situation like this? Good. Yeah, so Caden says I can swap the x and y and then get the y by itself again. I prefer to do it in the opposite order. I like to get the x by itself and then swap the x and y. There's not really much of a difference there. The one place where doing it my way can become a little bit easier is if you have a situation where there's an implied domain. That information tends to make more sense in what to do with it if you do the swapping second after you've isolated the x. But the vast majority of the time, it doesn't even matter which order you do that in. So there's really probably no difference there. I would say there's one other thing that we should do, though, before we do any of that. And we should replace f of x with y. Notice there's no y in the one that we wrote there. Okay, so if we do this, replace f of x with y. To get x by itself, I'm going to add 7 to both sides, and then divide both sides by 3. And then if we swap the x's and y's, we can say that f inverse of x is x plus 7 over 3 Or if you wrote it as x over 3 plus 7 over 3, that's fine as well. 6 of one, half dozen of the other, they're both equally correct. Makes no never mind to me which way you wanted to represent that inverse. Everybody okay with what I've done so far? Okay. Hopefully this feels familiar and doesn't seem too difficult right here. And this is a pretty easy example. We'll look at some more complicated ones here in a moment. But we've made a biggest claim here, right? I've said that this and this are inverses. How do I know I'm right? What could I do to check that? Maya, you said what? You could graph and look to see if they look like they're reflections across y equals x. Now, how do you know that they're actually reflections across y equals x? What if they're just really, really close and it's hard to tell visually? Okay, Caden says you can find points and check to make sure that the transposition is there. But the inverse should be that for every point. Are we going to check all the points? You can't, right? Because typically there's going to be an infinite number, especially in this case. These are both excellent ideas, but there's a little bit of a shortcoming to each one of them. There's a third way that we can do this. If you recall back to the last lesson where we defined defined an inverse, let's look at that definition again. Where is it? Here it is. Look at what's included in that definition. A way to algebraically check if two functions are inverses, right? The definition says f and g are inverses provided that the composition both ways gives us x. So to check this, what I can do is I can do f compose f inverse of x, and also f inverse compose f of x. And the result I'm looking for in each of these compositions is they both simplify down to give me just x. So let's do the one I've written here on the left first. I know that f compose f inverse is the same as f of f inverse. And I'll just replace f inverse with its algebraic representation. So I'll just replace f inverse with the equation that it's equal to. That was the result from above. And then to do the composition, I'm going to rewrite f, but everywhere where there was an x, I'm going to write an empty set of parentheses. And then inside of those parentheses, I'm going to write f inverse. If I simplify here, the times 3 and the divide by 3, and then the plus 7 and the minus 7 cancel, and I'm left with just x. Now, just showing it for one of the compositions isn't enough. I need the inverses to work in both directions. I need f to cancel out f inverse. I need f inverse to cancel out f. So I also have to check the other direction. So I'll do that here quickly. And we see that that works as well. So now I know for sure that these two things are inverses. They meet the definition of an inverse, the strict algebraic definition of an inverse. So I'm sure that I'm correct, that I did or found this inverse correctly. Everybody happy with what I've done here? Okay. Now, this example was quite straightforward algebraically. There was nothing tricky about it. We, in fact, gave you about the easiest possible situation where our function was just a linear function. So none of the solving or isolating or simplifying was terribly difficult. Let's look at another example where things get a little bit algebraically messier, to just review a few of these skills that we saw last year in Algebra 3-4. So let's say this time our function was defined as 2x plus 5 over 5x minus 8. What kind of function is this again? It has a kind of a name, starts with an R. Rational function is the kind that this is. Good. So let's find the inverse, just like we did before. So I'll start by replacing the f of x with a y. And then what do you think we should do first here? Maya, you said multiply both sides by 5x minus 8. Sounds like a good idea. That's going to clear the fraction out of there. Equivalent to doing that is if you cross-multiplied, if anyone was thinking about that as an answer. That's doing the exact same thing, in this case anyways. Both of those are perfectly appropriate. It tends to make life much easier to get rid of the fractions whenever possible. What do you think we should do next? Anybody with an idea here? I'll tell you what I would do next. Distribute that y. You should have said it then, Kate. You could have gotten some credit for it. You could have done your little right answer dance and fist pump like Trevor did earlier. That's your thing, though. Yeah, that is your thing. But might do it better as she copied it. All right. What now? Anybody with an idea? The issue here is that I have x's in two locations, right? If we're trying to get x by itself, that makes life a little bit difficult. What I would do next is I would move the x's onto one side and the non-x's onto the other side. So I'm going to subtract 2x from both sides and then add 8y to both sides. And if I look at the left-hand side now, still have x's in two locations, but I notice that both pieces on the left-hand side contain a factor of x. If I factor a greatest common factor of x out, I now have x in a single location. Everybody see what I did there? That's the trick to this kind of problem. If you have a rational function and you're trying to find its inverse, you almost always are going to have to do this factor out an x. I'll now just divide both sides by 5y minus 2. And then if I swap the x's and y's, I have my inverse. Any questions about what I did there? So what's the sneaky step? It's going from there to there, where you have to get the x's on one side and then factor an x out. Easy to forget that that's something you can do. Now suppose that I wanted to verify that f and f inverse are indeed inverses. Again, the composition that we have to do there can get a little bit tricky, so let's kind of review that, if for no other reason, just like an algebra skills review, because there's some neat tricks that we can use to deal with that. So I'm just going to write down again f and f inverse here real quick, because they were awfully spread apart on my paper, so it wasn't going to be realistic to be able to project both of them on the screen at the same time. So let's do that check here. So to check to see if they're inverses, I have to do the composition both ways. So I have to look at f of f inverse and then f inverse of f. So let's do this one on the left first. So I'll start by just replacing f inverse with its algebraic expression. And then to do the composition, the way I like to do it is I like to start by writing my equation for f, but in place of wherever there was an x, I'm going to leave an empty set of parentheses. And then inside of that set of parentheses, I'm going to write my f inverse. Everybody okay with this? Okay. This is a particularly nasty looking expression here that we have to simplify. We had a name for this kind of thing in Algebra 3-4, was two-word name with the initials CF. Does anybody remember what we called these sorts of things? What was that? Somebody said it. Complex fraction is what we called this. Yeah, well done. So when we have a fraction inside of another fraction like this, we call that a complex fraction. This is a potentially lengthy simplification process. There is a neat trick, though, that we can use to shorten the simplification up considerably. So the trick here is I'm going to look at the denominators in the subfractions, and I'm going to find the least common multiple of those denominators. Since they both are the same denominator, that least common multiple is just 5x minus 2. I'm going to then multiply this fraction by 1, but the way I'm going to write the number 1 is I'm going to write it as 5x minus 2 over 5x minus 2. Since I'm just multiplying by 1, it doesn't change anything. I'm free to do that as I like. So when I distribute that 5x minus 2, when I multiply to the first term, the 5x minus 2 in the denominator cancels out the 5x minus 2, and I'm left with just 2 times 8x plus 5. And then I have 5 times 5x minus 2. When I multiply the 5x minus 2 in the denominator, the 5x minus 2 cancels the 5x minus 2 in the subdenominator, and I'm left with 5 times 8x plus 5. And then I have the minus 8 times the 5x minus 2. notice in doing this, what did I get rid of? All of the subfractions, right? We're just left with now polynomial over polynomial. So all I'm going to do here is just distribute things out and then combine some like terms and reduce. When I do that, I get 41x over 41, which just gives me x. And I'm done. So just to reiterate how nice of a time-saving shortcut this is, if you had not done this, you would have needed to make a common denominator in the numerator and denominator, add the fractions in the numerator and denominator, and then divide the fraction in the numerator with the fraction in the denominator. You're talking like 3 or 4 extra steps that are all pretty terrible, as opposed to this one step that I did here that kind of cleaned everything up considerably. It's a nice little shortcut for those situations. I'm going to let you guys do the other half of this right now. So go ahead in your notes to do this other half of the composition. Try to use the same simplification trick that I just used on the first half. Yeah. Okay. So, do you see why I chose 5x minus 2? So, you see in the subfractions, that's why I chose 5x minus 2. Yep. You see now what happened? Okay. All right, so what do we have here? Yes. Nope. You're checking to make sure that these two things are inverses. So you're doing the composition listed here. So I skipped some steps kind of in between there, but that's me doing the shortcut simplifying. Check Power School. I posted the assignment, or the next assignment there. I think it's 31 through 42. I apologize on the length, but most of them don't require any calculation. You're just writing stuff down or saying if it's one-to-one or onto and stuff like that, where it's not a lot of calculation, but you have to think a little bit about what those definitions mean. Right, because we don't meet tomorrow.